All right, oriented surfaces. Well, first of all, oriented, we might remember that general definition is we need to specify a direction. Ooh. And so remember when we were discussing curves, we said an oriented curve was just one that had an arrow on it, right? We have to specify the direction of parameterization versus if we just had a generic line, we didn't have to specify direction. So just remember that. So we talk about an orientation on a surface. So the surface has to be smooth and connected, right? And then the orientation is a choice of a unit normal vector at each point of the surface. Okay, and the idea is that we do this so that we can have the vectors vary continuously. But generally they all point outward, they all point inward, they all point sideways, they all point diagonally. There's some common orientation to the entire surface. Okay, so then if we think about a sphere, okay, again, what you want to do is want to think about, okay, for a given point, how many different possible normal vectors are there to that surface, and I'll let you take a moment and think about this. So again, you're taking different points on the sphere and you're saying, okay, well, what are the normal vectors at that point? Well, you could have outward pointing normals, certainly. And I think the only other choice would be to have the unit vectors point inward. So I believe that the answer here is 2. Okay? And so then this is kind of a nice question, but if you have a smooth, connected, orientable surface, how many orientations are there? Well, so think about a cube, think about a cylinder, think about a pyramid, think about, I don't know, a paraboloid. 2. It's always going to be 2. Okay, that is a fact. Okay, but then now I say that, but then are all surfaces orientable? Maybe, maybe not. Can you give me a counterexample? Why, yes, I can. I can give you 2 of them. Okay, you might have seen these surfaces previously. They are famous in mathematics, and one of them they're both very interesting topologically. So if and when you take more advanced mathematics, which I encourage you to do, these are going to pop up all the time in topology, which is the study of surfaces and their features. Anyway, actually, it's a study of sets, and yeah, anyway. So when you think about this, well, okay, Mobius strip. So this is a Mobius strip. And I think there's an umlaut over the O. So it's Mobius strip, or something like that. I used to know. I don't remember anymore. But Mobius strip, the idea is that you could look at a path and it would go along like this, and then go along like this, and then eventually you would end up on the inside, and then you'd go along that, and you'd end up on the outside, and then you'd come back to where you started. So you can walk continuously and see both, quote unquote, both sides of the surface. Well, if you do a normal vector here, that is pointing maybe outward, but then when you do it over here, it's pointing inward, right? So this one doesn't have an orientation. The second example, this one is less commonly discussed, but perhaps more famous in other ways. This is called the Klein bottle. Because there's no way to get to the inside is the outside. Because if you pour liquid in here, well, then it comes in this tube and out, and then it's actually the outside, so it's really weird. Anyway, again, if you look at taking a point on here and find the normal vector. Okay, in or out, or sorry, out or in, and then you follow that through. Then eventually, that is going to be on the interior of the bottle. So your outward pointing normal vector is actually pointing inward, and then your outward is pointing, or your inward is pointing outward. So the orientation isn't consistent. Okay, so this one is not orientable. Okay, so just some kind of fun examples with orientation, and then we'll do an example, talk about reparameterization, and we'll be done with videos for this week.